Okay, good morning. Let's begin. Today, we are going to keep on talking about chapter 2. We are going to be talking about a little bit of a number theory. We are going to be talking about modular arithmetics and more interesting stuff. But before we move on, do we have any questions? Now, on administrative portion of the class, we are going to have a traditional synchronous class today and on Wednesday. However, on Friday, we are not going to meet synchronously. Instead, I'm going to post lecture for you to view. Okay, I have another commitment. I am volunteering at a conference during that time and giving a talk, and I cannot be at two places at once. So I'm going to just post it. Please watch it at your convenience, but definitely before the Monday to make sure you know everything you need for the Monday's lecture. Okay. So let me start sharing my screen. I don't see any questions. So hopefully that means there are no questions at all, and we can move on. Okay, are we going to have a coin flip on Friday? Yes, we can flip a coin on Friday. It's going to be a bit more complicated due to the fact that I'll have to record it ahead of time, but I'll think about how we are going to do it, okay? Now, so we are in chapter 4, and the last thing we talked about was the division algorithm. So we discussed that given a number A and B, oops, both of them integers, B is actually positive, A can be represented uniquely as B multiply Q plus R, where Q is quotient, R is the remainder, and R must be in between 0 and B. Okay, so what we need to talk about is the remainder. Actually, it gives you the remainder when you divide one number by another. We're going to define a function called mode. In programming, we specify it as a percentage function. Now, the quotient actually generally given using integer division. Or in Python, it's going to be double slash versus one slash division. This is an integer division type of thing. So this is a function called div. So Q is equal to A division B, and R is equal A mod B. So let's talk a little bit about what we did and proved last time. Last time we said that this representation is unique representation. And we actually constructed our proof by showing how it must fall someplace. So today we're going to talk about so-called modular arithmetics. Modular arithmetics used a lot in computer security, and it has tons of interesting properties. So let's define a couple of things. If A and B are integers, M is integer such that M is bigger or equal to 0, positive integer, then we say A congruent B modulo M if M divides A minus B. The notation is going to be A congruent B mod N. So the congruence is 3 lines instead of 1 line. Now, this means A congruent B mod M. If you want to say not, you're going to cross the mode. This is going to say mod M. A is not congruent B mod M. Example. So, for example, we are comparing 3 and 10 mod 2. Are they congruent or not? So actually, another way of thinking about mod function is comparing the remainder. If the remainder is the same, then they're congruent to each other. So how much is 3 mod 2? Three mod 2 is 1, correct? How about this 10 mod 2? Are they equivalent to each other? No. So what we need to put here is they're not congruent to each other. Now let's check. How does it come to our definition? Well, let's look at A minus B. This is 7. Does 2 divide 7? The answer is no, correct? 2 does not divide 7. So this is totally fine. So here is the deal. We do not write mod 2 on both sides. The 3 is still mod 2, but we do not write it. In order to be congruent, they need to have the same remainder, mod that number, but we do not put it on both sides. It's kind of like a notation thing. So we do not really write 3 mod 2 is congruent to 10 mod 2. We just write 3 congruent, 10 mod 2. But if you see mod on one of the sides, that the same mode has to be on the second side too. So let's do another example. What about 5 and (25) mod 4. Are they congruent to each other? So what is 4 mod 4? Yes is correct answer. The reason for it is 25 minus 5 is 20, and 20 is divisible by 4, correct? So all good. But another way to see it is 5 mod 4 is equal to 1. And 25 mod 4 is also equal to 1. So that works like a magic. So those two are the same. This brings us to a theorem, which I have been using already and showing you. Let A and B be integers and let M be a positive integer, then A congruent B mod M if and only if A mod M is equal to B mod M. Now, I'm sure many of you are now confused with 3 lines versus 2 lines, equal versus congruent. Remember, those two are 2 different operations. So in here we have congruence, and the mod M is kind of a default one you remember about. You don't even write it. That's a congruence, correct? But in here, after you do mod, this number has to be exactly same number. This is 1 equal 1 or 5 equal 5. After we apply mod operation, you always get the unique remainder, correct? The remainder is unique. So in this case, you really need an equality for it, okay? So if you think about it, and the exercise on the top, I can say 5 is congruent 25 mod 4, but 5 is not equal 25, correct? So it's not really equal 25 mod 4. What we can also write is we can write 5 mod 4 is really equal to 25 mod 4. Why is it really equal? Because we have 1 here, and 1 is really equal 1, correct? So that's a big difference between congruence versus equality. Congruent means the remainder will be the same. And then the equality is actually when you have an exact same number, and you do need to write mod on both sides if you want to use equality. Okay. Now, a couple of rules on how you can manipulate the modes and a couple of, like, theorems. So let M be a positive integer and A, B be integers if A mod M and B D mod M sorry, I don't like my parentheses. I'm just going to write mod m and a, b, c, d are all integers. Then a plus c is congruent to b plus v mod m, and AC equal to BD mod. And this is theorem, yes? A rule you can use. How can you prove something like this? You can put BD in parentheses or not in parentheses. Actually, multiplication is going to win over the mode. So in the order of, precedence, it should be fine. So you first do multiplication and then you apply the mode. So how do we prove a thing like this? Let's do the first portion. Let's look at B plus D, which is congruent. Well, since B is congruent A, you can say that it's congruent to A mod M plus C mod M. What does it mean that it is A mod M? It means as the same, this whole thing is the same as A plus some number multiply M. So you can represent B is A plus S multiply M. And you can represent D as C plus T M. Why? Because the same, remember, our definition is saying B minus A is going to be divisible by it, correct? So by definition, if you have A congruent B mod M, A minus B is divisible by M. So by definition of divisibility, it's going to be A minus B is equal to S multiply M for some integer, correct? Which is the same as saying B is equal to A minus SM, but take instead of minus SM positive KM, where K is negative S. You kind of like the sign here plus minus is not really important. Does it make sense? Because I can replace negative S with K, where K is equal to negative S. So the sign here is not important, but what we can say is, there's no mouse, yes, oops, sorry. So what I do here is I say, this is what I'm using in those parentheses out here. This is my star. So using the star, I can replace it, correct? And I can do a thing like that for some st integers, correct? They exist. But this is actually the same as saying b plus d minus a plus c is divisible by m, correct? So that's by definition, meaning it is same as s plus c, correct? So this is a proof of part A. This is proof of rule 1. You can see the proof of rule 2 in the textbook. So now let's do one more corollary. Remember, corollary will come directly from the previous theorem. Let m be integer m bigger than 0, a b integers. Then I'm saying a plus b mod m is the same as doing a mod m plus b mod m mod m, and then a b mod m is the same as a mod m multiply b mod m, and then mod m on all of it. Okay, and that brings us to operations on how we can play with numbers. So let's do an example. Assume I want to compute something like, let's see, 25 plus 39 mod 4, for example. Okay. So 25 mod 4 is 25 mod 4 is 1. And 39 mod 4 is 3. Now, can you understand why I need to do mod 4 one more time? Because the result of 2 mods is going to be in between 0 and m. However, after you add them together, sometimes you might overflow, correct? And not get number between 0 and m. And you always want to end up with calculating it so that the final answer is in between 0 and m. Does that make sense? So in this case, now what we're going to have is 4 mod 4. Why does it disappear? Which is just 0. Now, let's try and figure out why didn't I want to add. Well, if I'm going to add, I'm going to have 25 plus 39, which is going to be 50, 64, correct? 64 mod 4. The larger the numbers are, the huger the numbers I'm going to get, correct? So pretty much it's going to be less and less convenient if I'm going to try and do large numbers. It's going to be especially true if I want to do 25 multiply 39, correct? This is where you'll kind of need a calculator. Come on. Sorry, I don't know. My dot is disappearing for some reason. Here's my dot. Here are my lines. Good. So in this case, what's it easier? To compute 25 multiply 39 first and then try to mod 4 it, or do the mod 4 on each side first? What calculation is going to be easier? Do the mod first, correct? So pretty much this is going to give me 1 multiply 3, which is easily done in head, correct? Now, doing 25 multiply 39 is pretty ugly, and then dividing it by 4, it's probably also not going to be too beautiful. Now, those things become really handy if you have things like this. So assume I'm going to take, I don't know, 24 to the power 15 multiple, actually let's do plus 31 to the power 7, and I want to figure out how much it is mod, I don't know, 5, for example. Okay, does anybody really want to do 24 to the power 15? Or should we use our rules and make life easier? The rules are better, correct? So what we can actually do is we can say, okay, it's the same as 24 to the power 15 mod 5 plus 31 7 mod 5, correct? Then I can kind of take the 15 out of my parentheses. I can really say that it's 24 mod 5, and then I take power 4. I still need to remember to do mod 5 after. And then similarly over here, the same as 31 mod 5, and then taking it to the power 7. And I'll still will need to do the mod 5 on everything and mod 5 on both editions after. So mod 5 is going to be added everything. Every time you do it, you do an extra mod 5 just to make sure you're good. So how much is 24 mod 5? It's 4. So it's 4 to the power 4 mod 5. Yes? Oh, why is it to the power 4? I have no idea. It should be to the power 15. The power doesn't change. Yes, sorry, it is 15. Yes, it's just consider it being a typo in writing. Now, how much is 31 mod 5? That's 1, correct? Well, we have at least one good thing happening, correct? We can definitely get rid of 1 to the power 7, right? At least something. 1 to any power is just 1. So what do I do with 4 to the power 15? This is where I can kind of say, okay, I can say it's the same as 4 to the power. It's like 4 multiply 4 multiply 4 15 times, correct? Right? So it's the same as saying it's 4 multiply 1 multiply 4 to the power 14. Do you agree? Correct? And 4 to the power 14 is the same as 4 squared 7. Do you agree? And then we again have the mod 5 everywhere. So what I'm going to do is I'm going to leave my 4 here as is. And then I'm going to do 4 squared, which is, how much is 4 squared? 16 mod 5 to the power 7. Okay? So 16 mod 5 is 16 mod 5 is 1. Congratulations to us. We got rid of another part, correct? Now, it's not always going to be 1 and so nice, but a lot of times it is going to be a much smaller number. So this whole thing is just 1, correct? And 1 to the power 7 is just still 1, correct? So what I really have is I have 5, 4 mod 5 plus 1 mod 5, and then mod 5, which is, guess what? 0. So the good thing about modular arithmetics, you're always going to stay within small numbers. You're going to kind of make your large numbers smaller. You're always going to end up in between 0 and m, 0 inclusive, m exclusive. Now, one thing is, sometimes instead of writing the load mod 5, mod 5, mod 5 so many times, sometimes we might write something like 7 plus 9, and we do the 5s out here. And this is kind of meaning mod 5. This is another, sorry, it's not here, here. So this is going to be, I do 7 plus 9 mod 5. So 7 mod 5 is 2, 9 mod 5 is 4, so 6 mod 5 is 1. Okay, it's a great question. What is going to be quicker for computers? Should they compute the traditional, like to the power 15, or should they do the modular arithmetics? Now, if there is a modular arithmetics involved, most of the times it's much simpler to apply the modular arithmetics algorithms. Now, with the computers, we also have another problem. So let's talk a little bit about integers in programming. So those of you who are studying Python, you do not see it as much because in Python, you can do any large integers you wish. However, if you have ever dealt with C, C++, or Java, you would know that most integers must fit into 256 bits. What is a bit? Remember our string bits? Our string bits is 0 and 1s combined together, right? So what a 256 bits string means is I literally only have 256 spaces out here. So the largest number I can store in this amount of space is where I have ones everywhere, correct? So pretty much the largest number is going to be this, right? This is going to be the largest number I can put into computer for the integer for Java, for traditional integer. And if you think about it, the same, what did I have there? 29, if I'm going to put it even to the power, probably, let's see. Well, even if I'll do it like that, who is going to be larger? Which one is going to be larger? The 29 to the power 100, correct? Will I be able to store it? Will I be actually able to compute it without modding it? The answer is kind of not with the traditional integers. However, there are different libraries of how to store it. In Python, you still should be able to do it, but generally not to deal with huge numbers. If you have modular arithmetics, it's always better to apply mods first. Only if you are in modular arithmetics. That only works for mods, correct? It doesn't work in traditional numbers. If somebody gives you, you need to compute 29 to the power 100, you have to compute it the way it is, correct? We only have some rules about traditional, those rules are only about modular arithmetics. Now, you already know your homework assignment from this session. It's already posted. It is due Friday. Play with it. And we are going to go into section 4.2, and we are going to continue talking about integer representation. Oops. Okay, so what's going on? Theorem. Let B be integer B is bigger than 1. For all n in Z plus, n is equal to AKBK plus AK minus 1 BK minus 1 plus A1B plus A0, where K is non-negative and A1, A2 up to AK are all integers and bigger than 0. This representation is called B expression of A. Sorry, of M. Okay. So let's do an example. Okay, there's no why it writes the way it does. Give me 1 second. Let me restart this thing. I don't know why it's behaving so strangely. Let's check if now it's going to write better. So let's pick up N. Let's do it 100. And let B be, I don't know. No, it still does it. Okay. This one's supposed to be very familiar to you. And actually, instead of 100, let me do 1981. Okay. So now, what does that mean? So 1981 is equal to 1 multiply 10 to the power, what is 1000? 3 plus 9 multiply 10 to the power 900 is 9 to the 2. Great. And then 8 multiply 10, which is 80, correct? And finally, 1 multiply 10 to the power 0. If you look at what I have on top, correct? And what I have in the exercise, that's exactly it. This is the 10, this is the 10 expression of 1981. Did you do something like that at school? Probably even elementary school, correct? When you kind of think about it, I have a place of thousands, I have a place of hundreds, I have a place of tens, and I have a place of units, correct? Ones. So in this case, we are expanding it using the powers of 10. So we are saying how many of which ones we have. And why is it important and interesting? This is 10 to the power 1. Yes, did I wrote zeros there? Yes, it is 1. It's just 10. Yes. So this is interesting because I can do it for any number B. So what we can do is we can do something very similar and represent 1981 as an expansion of, for example, 2s, okay? Or 16s, or any other number. And this is important because it brings us to the idea that numbers can be expressed in different bases. So using different enumeration systems. So we are going to talk about binary numbers, octal numbers, and hexadecimal numbers. Binary numbers are base 2, octal numbers are base 8, and hexadecimal numbers are base 16. Yes, Zach, you're right. This is exactly how we convert between bases. We really represent numbers as different bases to the different powers and how many times it fits in. And you're going to see it in a second. So what we're going to do is we're going to generate a huge table. So we are going to have our traditional decimal. In decimal, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. After 9, I ran out of digits, correct? So what I really need to do is I need to open up a next placing, correct? So I add another number to the left of it. And I'm going to write 110. Really, if you think about it, I'm iterating all of my digits because now what I'm going to do is I'm going to increment the right digit by 1, correct? And keep on going. Agreed? Yes. The same idea is going to work for all the other enumeration systems. So let's talk about binary. In binary, we only have zeros and ones. So that means we will need to iterate very quick. So we are going to start with 0 and we're going to start with 1, but now I don't have any more digits to use. When I do not have any more digits to use, I'm out of numbers I can put in there. I need to open a new spacing to the left. So I'm going to say 1, 0. So 1, 0 is a 10, but actually it's a 2. I'm sure many of you saw those beautiful t-shirts with computer science jokes when just the 2 of us, and it says just the 10 of us, correct? And if you think about base 2, it's a 10. If you think about tradition, it's a 2. If you so pretty much there are tons of jokes on that point of computer scientists thinking about binary numbers. So for the fee, I still have an option of doing 1, 1, and this is what I'm going to do. And now, again, I used all possible combinations of 2 digits, correct? So I need to open up a new space, and I'm going to have 1, 0, 0, and I'm going to be iterating. Okay. Okay, so we have 1, 0, 1, 1, 1, 0, 1, 1, 1. And here I need to open up another one. It's literally similar to how we draw the truth tables, remember? Those are the same iterations. You always start from the right. And this is where we get 1, 0, 0, 0, 0. Now, for the octal, we are going to have 8 options. So we're going to have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Like that. Yes, they look ugly, but that's the way it is. And hexes, and I know I'm running out of time, are actually base 16. So I'm going to write 6, 8, 2, and 10 out here. And I'm going to quickly just tell you that, of course, when I get to the 9, after that, I do not have any digits like in numeration system we have. So 10 is actually A, 11 is B, C, D, E, F, and then you have 10 for the 16. So next time we're going to talk about how this theorem of bases is going to help us out. On that note, we're done for today. You should look at that more carefully and understand how the things work and see how it's like different bases. And then we're going to talk about this theorem from the previous, this theorem over here and how it helps us converting. Have a good day.